This chapter is called Conduction of Electricity in Solids. In fact, we'll start to understand many of the quantum mechanical properties of solids and some of the special ways that certain materials called semiconductors can conduct electricity and cause many special effects that are the basis of computers and many other things in modern technology. We're going to focus on solids that have a definite crystalline structure. That means if you look closely at the arrangement of atoms, they are arranged in some unit cell which then repeats itself. So I could take this and draw another one right here. So I could go there, 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 there. Now this here is the crystalline structure for copper. It's known as face-centered cubic. So you see here we have the dark red dots representing the carbon atoms that are at the corners of a cube. I could draw more here, 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 and here to finish up the next cell. And here, in the center of each face of the cube, we have another carbon atom. So in the next cell over, I could draw those here, 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 one in the back, one in the front, and one on the bottom here. I also want to point out that even though any way we isolate a unit cube, we have to choose corner atoms and face atoms, in reality, I could draw the corners of my cubes between these two and between these two, and so on. This would become a corner, a corner, a corner, a corner, and this one that was previously seen as a corner would be seen as a face atom. So it's not as if the individual atoms actually have a special role. They all can be viewed either as face atoms or corner atoms. This is the crystalline structure for diamond, as well as for silicon and many other semiconductors. Again, we have the face-centered cubic, shown by the darkest blue atoms at the corners and the lightest blue atoms at the faces. But there are four more, here, 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 and here, which allow us to have a tetrahedral structure. And then the next cell over would connect this tetrahedra for this corner, which is not, for this corner, which is not currently bound into either of these four tetrahedra. We're not going to focus a lot on specific crystalline structures. It's just important to understand that different chemical compounds have different structures. In fact, sometimes we can have different structures for the same chemical compound. For example, diamond and graphite have the same chemical structure but very different crystalline structures and therefore very different electrical properties.